Very good afternoon to one and all, and I welcome you all for the next not a lecture, the first practical of this semester related to the heat transfer, that is thermal conductivity of a insulating powder. Okay, so please let me know whether my voice is audible and can you see my presentation.
Yes, sir.
Great. Within a minute, we will start. Some students are joining. We'll wait for 1 minute. Okay, so today we are going to discuss about thermal conductivity of an insulating powder. Okay. Initially, I would like to describe that there are very uh, very high variety of material available on our mother earth. Okay, and there are different properties with the different materials, and these materials are using we are using for the different applications. Okay, now some are used for the heating purpose, some are used for the cooling purpose, some are used to avoid the heat transportation, some are used to increase the heat transportation or uh, heat transfer rate. Okay, but which property which very much useful to understand that the material is good conductor or good insulator is nothing but the thermal conductivity. Thermal conductivity of a material is one of the property which shows its value shows the ability to transfer the heat from one place to another place within the material, or one region of a material to the another region of material within that particular material. Okay, and we have discussed that the conductors or the heat conductors, we can say that the metals are the good heat conductors as well as the electric conductor. Why? uh, if you speak about its heat transportation, okay, the ability to transfer the heat from one region to another region within the same material, that is high for the metals because of its available free electrons and the lattice vibration. Whereas in case of non-metals, okay, let us take the number of examples are there. Plastic is there, wood is there, some bricks are there, building materials are there. Okay, there are n number of materials which are bad conductor of heat. So these materials mostly are non-metals, which does not have the free electrons to transfer the heat from one region of a material to the another region of a material. So in that case, such a materials will be act as insulating materials or bad conductor of heat. Okay, the materials which provide the maximum amount of resistance to transfer the heat, that particular material will be considered as an insulating material. Okay, that particular material will be considered as a insulating material. Take the example of our home. Okay, uh, the walls of homes are made up of bricks and the cement. Okay, if you replace this walls by considering the steel material, okay, what will happen? It will happen. So this is the simple application. If you replace the bricks structure by the steel material or steel walls, in that case, in summer season, the most of the heat will be entered in your house, and in the winter season, whatever the coordinates present outside the house, that will be also entered in your house. Okay, so the bricks are the good insulators. Okay, one of the insulating material, brick is one of the insulating material because its thermal conductivity is very low. So what because of that particular bricks, uh, that particular bricks, whatever the temperature outside, we are isolated or somewhat isolated from that particular temperature, or our house becomes isolated from external environment. Okay, so that is the most important factor whenever there is a requirement to isolate any compartment. Okay, to isolate any compartment or any section, we have to use such a materials that will having that is having less thermal conductivity. Okay, so I think network issues there. One, give me 2 minute time, I will manage it. Wait for 1 minute. I will make the another arrangement because there is a network issue in the college. Huh. Now it is visible. Screen is visible. Please reply me whether screen is visible. Great. So we can disintegrate these types of material as the good conductors and bad conductors. The materials which are uh, uh, which is having the ability to transfer the heat very quickly. That materials are called as good conductors, and the materials which provide maximum resistance to transfer the heat, that materials are called as a bad conductors of a heat. And these materials are uh, also called as a insulating materials. Okay, we have discussed that thing in the first chapter, that insulating material which provide the maximum resistance to transfer the heat. Okay, in that case, the resistance offered by that particular material to heat conduct is very much high. So the insulating materials are having very much low thermal conductivity. Okay, so here some of the materials listed in experiment number 1, that is asbestos, having thermal conductivity 0.230, and the working temperature range is up to 20 degrees Celsius. Then plastic 0.580, wood 0.170, brick 0.230, concrete 1.279, then fire brick 0.140, mineral wool that is having the thermal conductivity of 0.047, then plaster 0.779, then rubber 0.163, then cork sheet 0.042, then glass 0.744, then urethane foam 0.020, fiberglass blanket 0.050. Okay, so here you can see that the wood is also used as a insulating material. Okay, so if you have visited international conference hall in the college, then you can see that the walls are covered with wood material, or we can say that uh, the wood materials, and which is having very low thermal conductivity. So in that case, we are trying to isolate that particular zone or that particular international conference hall from outside environment. So whatever the coolness created inside the room, that will be remain for a long time in that particular room only, if there will not be a heat leakage inside that particular room. Okay, brick is also there, then concrete is also there. Okay, then rubber material, plaster is also there. Plaster, most of the time we are using the plaster for covering the walls. Okay, or covering the ceilings. So in that case, this plaster, why plaster is used? Because it is having very low thermal conductivity. Okay, then rubber, cork sheet. Okay, then fire bricks. So fire bricks are used for the furnaces. Okay, which will be act as a covering for the furnace, and in that case, these fire bricks avoid the heat leakage from the furnace to the external environment. Okay, avoid the heat leakage from that particular uh, furnace to the external environment. Okay, so fiberglass blanket, urethane foam, these are also having the low thermal conductivities, and which will be act as a insulating materials. Okay, then in this particular experiment, we are performing the experiment on one of the powder, that is nothing but asbestos powder, and we are trying to determine the thermal conductivity of that particular powder. Okay, we are trying to determine the thermal conductivity of that particular powder. Okay, so without wasting too much time, I will jump directly to the basic figure of this particular experiment. Okay, so in this particular experiment, there is one sphere. Okay, we can say that the hollow sphere is there. Okay, so this is outer sphere. Okay, this outer circle is nothing but outer sphere, and inner circle is nothing but inner sphere. Okay, now inside that inner sphere, we have placed one heater. Okay, centrally placed one heater which will generate the heat. Okay, and whatever the space is present in between inner sphere and the outer sphere, in that space the complete space is filled with the insulating powder. Okay, complete space is filled with the insulating powder. So this dot diagrams, you can see dots you can see in the diagram, that are nothing but a insulating powder. Okay, now here in the diagram it is shown that the support is provided for that inner sphere from the bottom side and from the upper side to maintain the location of that particular inner sphere. Okay, now this is filled with the insulating powder. Now, how to perform the experiment, that is most important. We are providing the electric supply to this particular heater. So the heater main function is to generate the heat, okay, to convert the electrical energy into heat energy, okay. So that is the main function of a heater, and it will generate the heat, and it will transfer first of all this inner sphere surface, okay. On this inner sphere surface, we have placed 6 thermocouples, okay. 1, 2, 3, 4, 5, 6. These 6 thermocouples are placed on this inner sphere, which will measure the temperature of an inner surface, okay, which will measure the temperature of an inner surface. Also, now once the heat will generate by this heater, heat will be transferred to this inner sphere, okay. First of all, heat will be transferred to the inner sphere, and from this inner sphere, the heat will transfer to the outer surface of outer sphere, okay. Heat will transfer to the outer sphere. Now in between these two surfaces, the space, whatever the space is there, it is filled by uh, the insulating powder, and which will try to provide the maximum resistance to transfer of the heat, okay, to transfer of the heat from inner surface to the outer surface. Now the 6 thermocouples, more 6 thermocouples are placed on the outer sphere surface, okay, outer sphere surface. So here up to the 6 you can see here, and 7, then 8, 9, 10, 11, 12. So remaining 6 thermocouples are placed over this particular outer sphere surface, okay. Then what we have to do? First of all, we have to measure the input supply of electric current to this particular heater, okay. That is nothing but to measure this input supply, we have to take the reading of voltage and current, okay. We have to take the reading of a voltage and current, and product of voltage and current, that will provide you the heat input for this particular system, or for this particular heater, or how much amount of heat is generated by this heater, that will be equal to voltage multiplied by current, okay. And to measure this voltage and current, we require voltmeter and ammeter. Voltmeter function is to measure the voltage, and current ammeter function is to measure the current. So voltage will be measured in volt, and current will be measured in ampere, and the product of these two will provide you the heat supply or heat generated by this particular heater, okay. So once you measure the heat supply or heat generated by the heater, then the another part of measurement is nothing but to measure the thermocouple temperature, okay. These 12 readings we have to take at once, okay, at once, okay. So these 6 thermocouples are connected to the temperature indicator, okay, the temperature indicator. So thermocouple switch is there, okay, digital temperature indicator is there. To this particular digital temperature indicator, all 12 thermocouples are connected, okay, all 12 thermocouples are connected. Then digital ammeter is there, which will show you the current reading. Digital voltmeter is there, which will show you the voltage, okay, which will show you the voltage. And thermostat is provided to you to vary the heat input, okay. You can also vary the heat input for that particular heater. So in that case, thermostat is provided to you. By varying or by changing or by rotating the thermostat knob, you can vary the heat input provided to the heater, okay. You can vary the heat input provided for the heater. So first of all, you have to adjust the reading of voltage and current. Then you have to take the readings of temperature. Then you have to take the readings of a temperature, okay. So in observation, okay, first of all, we have to take the readings of a temperature. Now I will go directly to the observation table, okay. So observation, in observation, you have to first take the reading voltage and ammeter, that is nothing but V and I, okay. Then next you have to take the reading of inner sphere, okay, that is nothing but reading of first 6 thermocouple will provide you the temperature of inner sphere surface, and then you have to take the average of this particular 6 thermocouples temperatures, okay. You have to take the average of this 6 thermocouple temperature, okay. Now my question is that why we are providing the 6 thermocouples over the entire surface of an inner sphere and over the entire surface of an outer sphere, and why we are not providing the only one thermocouple to measure the temperature of the inner sphere and to measure the temperature of the outer sphere. Why we are doing? Why we are taking this 6 reading for the inner sphere and 12 readings for 6 readings for the outer sphere? Because we are taking the average of temperature. Okay, so the chances of error will get minimized. Okay, the chances of errors will get minimized. Now you can see here in this particular diagram, uh, in this diagram, so this heater is placed centrally. Okay, now if you say that the first thermocouple is near to the heater, then you will get the maximum temperature for the thermocouple 1. Okay, and this 5 and 2 thermocouples are somewhat away from the heater. Okay, somewhat away from the heater. So in that case, we'll get somewhat minimum temperature as compared to 1, 3, 4, 5 for 2 and 5 thermocouples. Okay, so in that case, which temperature we have to consider? Okay, for the surface of inner sphere. So that is the big question. So to solve that question, we are doing this, that we are taking the average out temperature for inner sphere, and similarly also we have provided the 6 thermocouples. So you can provide 6, 7, 8, 9, no issue. As you are going to increase the number of thermocouples, the accuracy will goes on increasing, because we are doing, finally we are doing the average out temperature for the inner sphere and for the outer sphere. So providing the number of thermocouples over the surfaces, it decreases the errors occurred in a calculation or in a reading, and which will increase the accuracy of performance. Okay, which will increase the accuracy of performance. So for that purpose, we have provided minimum 6 thermocouples over the inner surface of a sphere, inner sphere surface and the outer sphere surface. Okay, now once you have done the calculation, now how much time we have to take the reading? Okay, so that is most important question. How much time we have to perform this particular reading practice, or up to what limit we have to take the reading? Okay, first of all, remember that we are dealing with the steady state conduction situation over here. Okay, so in that case, we have to achieve the steady state. Okay, we have to achieve the steady state. So how the steady state will be achieved? Okay, we discussed in the lectures also. If the temperature of the system will not change with respect to time, okay, or any property at particular location will not change with respect to time, so in that case we can say that this particular property is at steady state condition. This particular property is at steady state condition. So we have to take the bunch of readings for a particular time, this 12 readings at a particular time. Then after 5 minutes or after 10 minutes, you have to take the second reading once again for the temperature, and check whether that the previous readings are matching with the next reading. If it is matching, then that particular reading will be your final reading, because the further temperature is not changing with respect to time. If the 10 minutes before reading is matching with the next reading, then we can say that we have achieved that particular steady state. Okay, we have achieved that particular steady state, and that final reading will be considered for the calculation purpose. Will be considered for the calculation purpose. Now, once you calculate, we have reached to the steady state level. Okay, and we have taken the input voltage current calculation. Then you can calculate the heat input, that is nothing but Q, which is equal to V multiplied by I. So that will provide you the heat input for the heater or heat generated by the heater. And for the calculation purpose, we have discussed that. Okay, the last part about the discussion is the calculation. Okay, how to perform the calculation. So first of all, we have calculated the average temperature for the inner surface. So that will be equal to Ti. Ti is equal to addition of all the temperatures of the thermocouples which are placed on an inner surface divided by 6. That will provide you the average temperature for the inner surface, and that will be considered as T suffix I, that is inner surface temperature. Then next T naught will be the addition of all the temperatures measured by the outer surface thermocouples divided by 6. That will provide you the average out temperature for the outer surface, that is nothing but T naught. Now further, how to determine the thermal conductivity of that particular powder? Okay, that is most important part. calculation part, we know that according to the Fourier's law, we know that Q is equal to minus K multiplied by A multiplied by dt divided by dr. Okay, that is nothing but change in temperature with respect to length. Okay, dt divided by L we are considering, but here dt divided by dr, because we are measuring the thickness in a radius. Okay, or the sphere is having the radius, and variation in the length or variation in the radiation we are measuring. So here we are taking Q is equal to minus K multiplied by A multiplied by dt divided by dr, that is nothing but temperature gradient. Okay, we know this particular formula on the basis of a Fourier's law. Okay, now here in case of in case of a sphere, the area can be written as 4 pi r square. Area can be written as 4 pi r square. And if you transfer this dr and r square term on one side, okay, and the remaining term if you kept on another side, then you'll get the equation as q divided by 4 pi k multiplied by dr divided by r square is equal to minus dt. Okay, minus dt. Now here if you take the integration, then you will get q divided by 4 pi k multiplied by 1 upon r suffix I minus 1 upon r naught is equal to ti minus t naught. Here we have provided, after taking the integration, we have provided the limits for the radius, that is inner surface radius ri and outer surface radius r naught, that are the limits for the radius. And for the temperature, inner surface temperature is ti and the outer surface temperature is t naught. So by providing these particular limits, we have to perform the integration, and that we have done in many derivations. Then q will be written as q final equation for the heat transfer rate in case of a sphere will be given as 4 pi k multiplied by ri multiplied by r naught multiplied by ti minus t naught whole divided by r naught minus ri. Now this r naught is the inner surface radius, r naught is the outer surface radius of a sphere, and ri is the inner surface radius of the sphere. Okay, and these values are provided in the specification. These values are provided in the specification. So radius of inner surface sphere is equal to 50 mm, and radius of the outer surface sphere is 100 mm. Okay, then the voltage range is provided for you for the ammeter, for the voltmeter, and the current range is provided to you for the ammeters. Okay, so temperature indicator range is also there. Then dimmer stat range is also provided. Then heater coil specifications are provided. Okay, 200 watt heater is used. Okay, so all these specifications are provided to you. So for calculation purpose, we required only ri and r naught. Okay, ri is given, r naught is given. Now in this particular equation, ri is known, r naught is known, ti and t naught we have to observe from the experiment, and we have to calculate ti and t naught at steady state condition. At steady state condition, and once we calculated this, just put up the values over here. Okay, in the form of a q k. This equation we will get in the form of a q, and we can convert this equation in the form of a k. Then k is equal to q multiplied by r naught minus ri whole divided by 4 pi ri multiplied by r naught inside the bracket ti minus t naught. Okay, so you can draw the observation table in this manner. Okay, so inner sphere readings you have to conduct. Okay, thermocouple number, temperature in a degree Celsius. Then we have to take the 4 5 reading at least to achieve the to achieve the steady state temperature. And then for the final temperature, for the final reading, we have to calculate the average temperature or a mean temperature. Okay, so in this manner you draw the table. Okay, you draw this table. Meanwhile, I will go to HMT lab for the performance purpose. It's okay. दिसते ना व्यवस्थित इथून असं इथून चांगलं दिसतं. So this is the sphere actually, and in that particular sphere, one extra sphere is placed over there, and in that sphere we have placed the heater. Okay. Now this heater is connected to the thermostat. Okay, this is the thermostat. By using this thermostat, we can vary the voltage input to the heater. Okay, we can vary the voltage input to the heater. So let us see how it will be varied. If you change location of thermostat, you can see here the voltage is changing, and similarly the current will change. Okay, so as we are going to vary location, the voltage will get changed and the current will change. So in that, this particular supply is provided to the heater, which is placed in that particular sphere. Okay, in that particular sphere centrally. Now here we can measure the current by using this ammeter. Okay, digital ammeter is there, so we can measure the current supplied to the heater by using this particular ammeter, and we can measure the voltage which is supplied to the heater by using the ammeter, voltmeter, by using the voltmeter. And to measure the thermocouple temperature, this temperature indicator is used. Okay, to measure the temperatures of a thermocouple, which is measured by the thermocouple, that will be indicate over here. Okay, now simply this to check the temperature, this thermocouple junction is provided over here. Okay, so it will be start from here, so T1, T2, T3, T4 up to T12. So these 12 junctions are provided. Okay, 12 junctions are provided, and this wire is used to measure the temperature. Okay, how to check that particular temperature, I will show you. Now once I will insert this wire in first junction. Okay, this black one and red one, these are the connections. If I when I insert the wire in this junction, it will show the temperature in temperature indicator. It will show the temperature in temperature indicator. Now it is showing the error. Let us see what will happen if I insert the wire in first junction. Okay, I have inserted wire in the first junction and it is showing the temperature 35.6 degrees Celsius. In a similar fashion, when I remove this wire from the first junction, and when I insert this wire in a second junction, okay, then I have inserted this wire in a second junction, then it is showing the temperature of a second junction. Okay, similarly, when I insert the wire in the third junction, it will show the temperature of a third junction. Okay, so in this manner we have to take the readings of a temperature. Okay, in this manner we have to take the readings of a temperature, and after taking the first reading, that is nothing but for all the 12 thermocouples, once we take that reading, that will be our first reading. Okay, then after 5 minutes we have to take once again another reading. Okay, once again another reading. First of all, we have to record the current and voltage. First of all, we record the current and voltage. Okay, and then it will be constant for throughout experimentation. Okay, it will be constant throughout the experimentation. So current, now current is 0.01 ampere. Okay, first of all record it, 0.01 ampere, and the voltage is 40 volt. Now it is somewhat fluctuating because the power supply which is coming from MSCB, that is fluctuating, and because of that it will be slightly fluctuate from 39 to 40. Okay, so voltage is equal to 40 volt and current is equal to 0.01. Okay, then if you make the table in this manner, T1, T2, T3, T4, T5, T6, okay, T7, T8, T9, T10, T11, and last one is T12. Okay, so first 6 are related to the inner sphere temperatures, and next 6 are outer sphere temperature. Okay, and then we will go for the readings. Okay, So first temperature, T1 temperature is 37. Okay, 37 point. 1 minute, 1 minute. Okay, you can record 37 point. It is changing, still it is changing. 36.6. Take the reading, first reading, T for the T1, 36.6. Then second one, T2, 37.3. 37.3. Then fourth one, third one is 36. 37.3. Fourth one, it is fluctuating in between 37.6 and 37.3. You can take in 37.6. Okay. The next one, T5. T5 is 37.4 or 37.7. 37.7. 37.7. Okay. Then next T6, the last temperature reading of inner sphere. 37.7. Okay, so in this manner we have completed the readings of inner sphere. Okay, first reading of inner sphere. In a similar manner, now first set is completed. Okay, now there is gap and second set is started. Okay, this second set is for the outer sphere. This second set is for the outer sphere. So we will start for the outer sphere first reading. So let us see how much difference you are getting from the inner sphere readings and the outer sphere reading. How much? 37.8. Okay. Next. 38.1. 38.1. The next. Take 38 or T9. 38. T10. Take 38.2. Next. 38.2. T11 and T12 is last one is 38.4. Okay, this is about the first reading, and after 5 minutes, we have to conduct the another reading. Okay, if this whatever the first reading we have taken, if this reading is matching with the second reading, then we can consider that we have achieved the steady state level. Okay, if not, then we have to go for the third reading. Okay, in this manner, we have to continue up until and unless we will not achieve the steady state. Okay, steady state in this experimentation, steady state is nothing but the previous reading is matching with the current reading. Okay, previous temperature readings are matching with the current temperature readings. Okay, so it will require more time, nearly about uh, 1 to 2 hours to achieve this final reading. Okay, still I have started this experimentation, or I have on this experiment 1 hour before by current time. Within 1 hour we will achieve the final reading. Okay, so finally I will provide you the reading table in this particular manner. As we have discussed about the one reading, in similar fashion, I will take the four readings and final reading I will provide you, and then we will perform the calculation. Okay, so in this manner we can perform, and I will show you the calculation part. Whether my screen is visible? Okay. So first of all, you have to write the observations. So I will take here new file. Observations. You have to write observations. So first one is the voltage. So we have get 40 volt. Okay, and second one it's current, and we have observed it is equal to 0.01 ampere. Then you have to prepare one table, two tables. If you want to prepare two tables separately, then you can take in this manner table. So here you can use serial number 1, 2, 3, 4 in this manner, and here you can write also inner sphere reading. Okay, inner sphere temperature reading. Okay, and this will be merged. Okay, so inner sphere temperature thermocouples are T1, T2, T3, T4, T5, and T6. Okay, so in a similar fashion, outer sphere temperature reading table you have to prepare. Second table. Okay, and thermocouple numbers start with T7, T8, T9, T10, T11, and T12. Okay, so let us say that we are getting the steady state after 3 and 4 reading. Okay, so 1, 2, 3, and 4. Okay, the third reading and fourth reading are matching. Then the fourth reading will be considered as a final reading. Okay, then fourth reading will be considered as a final reading. So in that case, you have to consider, first of all, you have to calculate TI. Okay, TI, that is the inner surface temperature, which is equal to T1 plus T2 plus T3 T3 plus T4 plus T5 plus T6 divided by 6. Okay, whatever the answer you are getting, so that will be your final TI. Okay, that is the inner surface temperature. And in a similar fashion, you have to calculate the outer surface average temperature. T outer, okay, and it is equal to average of T6, T7, T8, T9, 7, start from 7, 7, 8, 9, then 10, 11, and 12. Okay, you will get this T outer and T inner. Once you get that, we know the Ri value and R naught value. Then you can say that from equation, once you know Ti, T outer, then we have voltage and current. Then Q is equal to V multiply by I. Okay, so here we are having 40 multiplied by 0.01. Okay, so from this equation you can calculate the Q. Okay, then also we know that Q is equal to 4 multiplied by pi multiplied by 4 pi k multiplied by R suffix I multiplied by R suffix multiplied by Ti minus T naught. Okay, Ti. Someone speaker is on. Please mute yourself. Ti minus T naught. Okay, so we know this equation divided by Ri minus R naught. Okay, so by putting, we know the value of Q, we know the value of Ri, we know the value of R naught, and from this observation table we will get the Ti and T naught values. Okay, we have to put up here. We can calculate the K value. Okay, so we can write the K as K is equal to Q multiply by Ri multiply by R naught whole divided by 4 pi see. Here I will remove this K because we are 4 pi Ri multiplied by R naught multiplied by Ti minus T naught. Okay. So by using this equation, we will get direct value of K. Okay. By using this equation, we will get direct value of K. So according to the given data, we are having, that is nothing but about the Ri and R naught. Okay. We are having Ri as 50 mm and R naught as 100 mm. So 50 mm means, and Q also we have calculated, which is equal to 4 watt, 40 multiplied by 4 watt, right? So we can put up here in this equation, we can put up Q as 4 watt, 4 watt, Ri as R naught minus Ri. It should be R naught minus Ri. Okay, so 4 multiplied by R naught is 500 into 10 raised to minus 3. So that will be 0.1 and R naught will be equal to 0.05 divided by 4 pi multiplied by 0.1 multiplied by 0.05, and if you just put up whatever the value you are getting Ti and T naught over here, you will get the value of K. You will get the value of K. Okay. Is there any doubt, any question in this particular experimentation? Whether you understood?
Sir, Q value.
Yeah.
Sir, Q value should be 0.4 now.
Okay. 40 multiplied by 0.4. Okay. Okay. 0.4. So here will be 0.4. Getting everyone how to perform the experiment and how to take the readings and then calculation about the thermal conductivity. Okay, so shortly I will provide you, if you have written this properly, okay, write down this. Okay, that will be your observation and calculation. This part will be considered as a calculation part. Okay, first of all you have to calculate Ti, then T naught, then Q will be calculated from the observation, voltage and current observation, and then we know this particular formula for the Q. Just put, we have converted this formula in the form of a K. Now just one value, two values are remaining, that is nothing but Ti minus T naught. Okay, we will provide you these two observation tables, but you should first of all you have to understood how to take the readings. Okay, that I have shown you how to take the readings by using the thermocouples and that particular temperature indicator. We have to take the readings, but that will require more time to conduct the readings. We have to wait for the 5 minutes for after each and every reading, and then we have to take the next reading. Then we can say that we have achieved the steady state temperature. Okay, if the current reading, whatever, if you say that the fourth reading, whatever I'm giving 40, for example purpose, I will provide you 36, 37, 37, 35.5, okay, 36, 40, okay, and here I'm getting the reading as 32, 33, 32.5, 33, 32.4 and 33. Okay, in this manner my previous reading is there, and I'm getting or near about, I'm getting the reading equal to 36. Next reading also I'm getting the same as that of a previous 37, 35.5, then 36, then 40, 32, 33, 32.5, 33, then 32.4 and 33. Okay, when I'm getting this in a similar fashion or near about accuracy, okay, if I'm getting that 35.9, okay, one of the reading it may vary somewhat. Okay, the accurate steady state will be considered, this will also considered as accurate steady state if one of the reading will slightly vary from the previous reading. Okay, so in this manner I am getting the next reading as that of equal to previous reading. So in that case I can say that I have achieved the steady state for this particular performance. Okay, and this final reading, this fourth reading, will be considered for the calculation purpose. This fourth reading will be considered for the calculation purpose. So here in this particular case, Ti will be equal to the addition of this all six readings for the six thermocouples divided by 6, and T naught will be equal to addition of this particular final six thermocouples divided by 6. Okay, and once you get the value for Ti and T naught, you have to put up this value in this particular K formula and you have to calculate this. Okay, so we will provide you this table shortly, and after that you can do the calculation. If you want to write this, okay, if you want to draw the table and calculation formulas, then you can do that. Okay, then I will share the write-up part with both the divisions related to our first experiment. Now here, don't write everything in this particular experiment. Okay, so you can write the introduction, name of the experiment, aim, introduction part, and this particular table you can draw. Apparatus you can neglect that part out of the write-up part. Then you can draw the diagram, and theory also you neglect about this theory part. Okay, then directly specification you write this specification, and neglect the procedure precautions, don't need to write. Then directly you go for the observations. Okay, then directly you can go for the observation. Okay, once again I will provide you this observation and final result in a watt per meter Kelvin, whatever the calculation you are getting after providing the observation tables to you. Whatever the calculation you are getting for the K, you just put up that calculation final answer over here in the result section. So once again I will tell you how which things you have to neglect and which things you have to write. Okay, once again, so you can write also. I will share this file. Okay, experiment number 1, provide the heading, then am, then introduction part you can write, then you can draw this table. Okay, need not to write the apparatus. Okay, apparatus part you can neglect. Then you have to draw this diagram. Okay, then you can neglect the theory part. Okay, no need to write the theory part. You write the specification. Okay, specification need to write this 10 specification. Then procedure you neglect, precaution you neglect. Then directly you can write the observation. Then this table you have to draw the table and write the readings. And finally you have to do the calculation and result, that much only. Okay, so hardly in 3 pages you can finish up the write-up part of a first experiment. Okay, in 3 pages you can finish up the write-up part of a first experiment. Getting everyone? Is there any doubt, any question? Okay, so we'll stop here for the today. And I declare that our first experimentation is over. I will provide you reading in and this particular write-up part uh, in your WhatsApp group. Okay, finish it as early as possible. You can put up your roll numbers in the chat box and you can leave this meeting. I'm going to close this meeting. Please leave the meeting or else I will end up the call. Remaining student, just put up your roll numbers in the chat box and you can leave the meeting.